the universe clearly expanded, stretching out endlessly. After a period of time, it continued to grow, but at a slower rate, eventually forming the universe we know today. This is known as the inflationary theory of the Big Bang, the most well-known and widely accepted explanation of how the universe began. However, some physicists believe that this theory doesn't fully explain the creation of our universe. They think that the universe existed before this event, stretching infinitely into both the past and the future. Even though the universe is still expanding today, it was actually shrinking in the past. In this view, the Big Bang isn't exactly a bang, but more of a jump or sudden event. Over time, the shrinking universe changed direction and started expanding again, following a different path according to this theory. The universe could keep expanding, but eventually, it might collapse, and then another jump could happen. Some physicists believe that this cycle of expansion and contraction could go on forever. The standard theory of the Big Bang, which says the universe began with a huge explosion, also has problems. Some things about it are hard to explain, especially how everything could have come from nothing. Recently, the James Webb Space Telescope has made some surprising discoveries that challenge the idea that the Big Bang was the start of everything. These findings have led to the question: if the Big Bang wasn't the beginning of the universe, then what was? Could the universe have started in a different way or from something else? The idea that the universe might have had a beginning without a past goes back to a scientist named George Lemaitre in 1927. However, proving that the universe had a definite start is still difficult. History doesn't seem to support the Big Bang as the origin of everything. Still, some scientists, even in the scientific community, are convinced that the Big Bang is the first event that led to all of existence. According to this view, the Big Bang wasn't the beginning of life as we know it today. In fact, there is a lot of evidence suggesting that the universe may not have had a single starting point, but this hasn't been fully explored, partly because there are no clear boundaries to define its beginning. Our universe is often described as having gone through an inflationary period before the Big Bang. The Big Bang is seen as the final event in the process of cosmic development. In the early stages, the universe was completely empty. There were no particles, only empty space. But space itself was filled with an enormous amount of energy at every point. Over time, this energy changed, forming patterns as the universe expanded. As the universe grew, these changes led to the formation of mass and matter. This process of change is a key feature of how the universe developed. It's not clear if, as the universe expanded, there were any places where expansion stopped or slowed down, or if space between objects simply grew larger. But we can try to understand what happened closer to the beginning of the universe, before the region where the Big Bang occurred disappeared from sight. This area was likely small, perhaps no bigger than a hamster ball, though possibly much larger. The energy in this small region transformed into matter and radiation. This change happened quickly, but not as quickly as the energy itself. It turned into photons and other particles, and the temperature rapidly rose from just a few degrees above absolute zero to about 20 Kelvin in a very short time. All the particles in the universe were moving near the speed of light, acting like radiation, whether they had mass or not. This transformation is called warming, and it marks the end of the early stages and the beginning of the Big Bang. As the universe continued to expand, it went through significant changes. While the Big Bang began, the universe's expansion slowed down. The energy that was once spread out became more concentrated. As the universe expanded, it left behind areas where expansion had slowed down or stopped. These regions eventually accumulated antimatter and radiation, growing more slowly than the already expanding areas. Over time, the space between objects continued to grow, but at different rates. In some places, the rate of expansion decreased, while in others, it continued to increase. The region we live in was lucky enough to experience a time when expansion slowed, but this doesn't mean all regions of the universe are the same. There's also evidence of small differences in temperature in the universe that challenge current models. For example, the light from the cosmic microwave background (CMB), which is the afterglow of the Big Bang, appears distorted as it passes through our galaxy. This distortion is not what we would expect based on current understanding, suggesting that something is missing in our theories. Additionally, the temperature of the CMB varies in a way that doesn't fit predictions about the universe's earliest moments. Finally, measurements of how fast the universe is expanding, known as the Hubble constant, change depending on how we measure it. These discrepancies suggest we might be missing a key piece of the puzzle about the universe's origins. One possible explanation for these anomalies comes from a theory called circle quantum cosmology. This theory is based on a concept called circle quantum gravity and proposes that there is a minimum size for space, much smaller than anything we can directly observe. According to this theory, the universe didn't start from a single tiny point, but instead, it could have gone through cycles of contracting and expanding. This idea suggests that the universe might have been reborn from a previous one, like a phoenix rising from the ashes. Though the idea of a cyclical universe isn't new, circle quantum cosmology provides a mathematical framework for understanding it. If this theory is correct, the early universe might have had lower energy and density than we currently believe. This could explain some of the temperature variations seen in the CMB and offer new insights into the universe's origins. Ultimately, circle quantum cosmology might help us solve some of the remaining mysteries in cosmology, providing a better understanding of the universe's beginnings. This theory offers a new way of thinking about the Big Bang and could help resolve some of the anomalies in current cosmological models. It also emphasizes the importance of continuing to explore the universe's origins and the theories that try to explain them. As we continue to explore the mysteries of the universe and the theories that explain its beginnings and development, we discover a complex tapestry of ideas and breakthroughs that challenge how we understand the origins of the universe. From the early days of the theory of cosmic detonation to current advances in cosmology and quantum physics, our journey to understand the universe has been marked by discoveries and ongoing questions. The theory of cosmic detonation, which emerged in the early 20th century, marked a turning point in our understanding of the universe's origins. It proposes that the universe began as a point of infinite density and temperature around 13.8 billion years ago. This theory of the Big Bang suggests that from this singularity, the universe rapidly expanded, and over billions of years, it cooled and evolved into the universe we see today. This idea, though widely accepted, still faces challenges as new discoveries continue to raise questions about its accuracy. Recent findings, like those from the James Webb Space Telescope, suggest that the universe's origins may be more complex than we thought. These discoveries push scientists to reconsider the classic Big Bang theory and explore new models of the universe's creation. Some theories, like circle quantum cosmology, propose that the universe might not have originated from a single point but instead could be part of an ongoing cycle of contraction and expansion. These ideas offer new ways of thinking about the universe's history and could help explain the anomalies we observe in the cosmic microwave background, CMB, and other parts of the universe. Understanding the true origin of the universe is one of the most fundamental questions in science. While the Big Bang theory has provided a widely accepted framework, it is clear that there is still much to learn. Theories like circle quantum cosmology give us exciting new possibilities to explore, and as we gather more data from advanced instruments and simulations, we may soon uncover even deeper insights into the universe's origins and the forces that have shaped its evolution. As we dig deeper into the fundamental questions about the universe's creation and structure, it becomes increasingly clear that there are still many mysteries left to solve. Whether the Big Bang truly represents the beginning of everything or whether there is a deeper, more complex story to tell, the journey of discovery continues. The universe, in all its vastness and complexity, holds many secrets, and with each new finding, we move closer to understanding the true nature of our cosmic origins. In conclusion, while the Big Bang theory remains the most widely accepted explanation for the universe's beginning, alternative models and new discoveries challenge and enrich our understanding. As we explore these possibilities, we gain a deeper appreciation for the vastness of the universe and the intricate processes that have shaped it over billions of years. The quest to unravel the mysteries of the cosmos is far from over, and each new theory brings us one step closer to uncovering the truth about our universe's birth and its ultimate fate. As we continue our exploration of the universe, it's important to remember that we are just at the beginning of uncovering its true nature. The tools we use to study the cosmos, like the James Webb Space Telescope and other advanced technologies, are providing new data that challenge our long-held beliefs and theories. These discoveries may lead to a deeper understanding of the universe's origins and its complex evolution. One of the most exciting areas of study is how the universe will continue to change. Theories like the expanding universe model suggest that the universe will keep growing, but there are also ideas that propose the universe could eventually stop expanding and start contracting again. This cyclical model, where the universe goes through phases of expansion and contraction, could offer new insights into how the universe works on a grand scale. Another major area of research is understanding dark matter and dark energy, which make up most of the universe's mass and energy but remain largely mysterious. These components play a significant role in the universe's expansion and structure, yet we still don't fully understand them. Unraveling the mysteries of dark matter and dark energy could change our view of the universe entirely, potentially revealing new aspects of cosmology and physics that we haven't yet imagined. There are also fundamental questions about the laws of physics themselves. Do they apply the same way everywhere in the universe, or could they change in different regions or at different times? Some theories suggest that the laws of physics could have been different in the very early universe, which would mean our current understanding of physics may not apply in those early moments. If that's true, it could completely reshape our view of the Big Bang and the evolution of the universe. The search for a unified theory of everything, an explanation that can combine all the forces of nature into one comprehensive framework, remains one of the most ambitious goals of modern science. While there has been progress in fields like quantum mechanics and general relativity, a complete theory that explains both the very small, particles, and the very large, cosmic structures, is still elusive. The discovery of such a theory could potentially explain many of the mysteries we are currently grappling with, from the behavior of subatomic particles to the vastness of space itself. In the end, the quest to understand the universe is not just about answering big questions. It's also about learning to appreciate the complexity and wonder of the cosmos. Each breakthrough, no matter how small, brings us closer to understanding the origins of everything, from the smallest particles to the largest galaxies. And with each discovery, we uncover a bit more about the profound beauty of the universe, revealing how much more there is still to learn. The journey to understand the cosmos is ongoing. Whether we are looking at the birth of the universe, studying the forces that drive its evolution, or seeking to answer deep questions about the nature of existence, science continues to expand our horizons. The mysteries that remain are as vast as the universe itself, and each new piece of knowledge we gain brings us closer to understanding the extraordinary nature of the world we live in. As we move forward, the exploration of the universe will continue to challenge our ideas, push the limits of human knowledge, and inspire future generations to look up at the stars and wonder. The universe holds countless secrets waiting to be discovered, and the journey to uncover them is one of the greatest adventures humanity has ever embarked upon.